Hey guys, Mr. B here, and in this video we're going to be going through the Chapter 14 review guide on work, power, and simple machines. So let's begin here with the first section of questions on 14.1, work and power. Number 1 says work is the product of A, speed and force, B, force and distance, C, power and force, D, motion and force. All right, so remember that work is going to be force times distance. We have the equation actually given right here. So it means that work is going to be a product of B, force and distance as our answer. So let's just highlight that in red. Number 2, which of the following is a unit of work? All right, so we have the joule, the watt, the horsepower, the newton. So the watt is a measure of power. Horsepower is a unit for power as well. Newton is the unit of force. And so the joule is our unit of work. Okay, so it's going to be A. All right, number 3. Which of the following statements are true about work? Include all that apply. So it says a newton is the standard metric of work. All right, so that is false. The newton is the metric unit of force, not work. Okay, so that is false, straight F, I guess, for false. A joule would be a unit of work. That is true. So that is the right unit. So true. Work is a distance-based quantity. It is dependent upon how far force displaces an object. That is true. So work is only done when a force is placed on an object and the object moves some distance. And the amount of work done, of course, depends on how much force is placed on the object as well as how far it moves. So yes, it is a distance-based quantity. An upward force is applied to a grocery bag as it is lifted from the trunk of a car. This is an example of work being done. So yeah, if you're applying a force upwards and the grocery bag is getting lifted upwards, then yes, you are doing work. So that is also true. A person holds a string of a yo-yo and applies a tension force as the yo-yo is moved in a circle around the world. Okay, so they're swinging a yo-yo around like this. This is an example of work being done. So this one is actually false. And the reason why this is false is because if you're swinging a yo-yo around in a circle, the motion of that yo-yo is constantly changing, right? The direction is constantly changing because it's going in a circle. And the force that you're applying is going to be inwards, okay, because you're swinging it like out, but then you pull downwards or you pull inwards to put tension on the string as you do this. So the direction of your force and the direction of the yo-yo is constantly changing all the time, and so the direction of the motion of the yo-yo and the force are not in the same direction, which means that no, you are not doing work in that example. So that is false. Number 4, which of the following statements are true about power? All right, so power refers to how much work is done upon an object. Nope. So power has nothing to do with how much work you do. Well, it does have something to do with how much work you do, but remember that power is the rate at which you do work. So it's not how much work is done, it's how fast you do the work. Powerful people or powerful machines are simply people or machines who are very strong. No. This is the common sense of the word that we're used to thinking of, right? You think of the word powerful and you think of being strong. But in physics, power, again, is about how fast you do something. It has nothing to do with strength. The standard metric unit of power is the joule. So we know that that's false because up here we had that the joule is a unit of work. So that's false. The metric unit of power is the watt, okay, not the joule. And then it says, a 75-kilogram boy runs up a 2.5 meter staircase in 2 seconds. His power is approximately 93 watts. So to calculate this, we're going to need to calculate the work done. Okay, so remember we know that power is equal to work divided by time. So we need to calculate his work. Okay, we know that work is force times distance. The force in this case is... I guess they're not giving us a force. Well, let's just pretend that the kilograms is a force. That's technically a mass, but whatever. So let's take 75 kilograms, or let's pretend it's newtons, times 2.5 meters. Just do this on a calculator real quick and get an answer. So 75 times 2.5. So we get 187.5 joules of work. Again, this is technically a mass, but I think that's a typo. Like, let's just change it. So, okay, so there's our joules of work. And then to do our power, we will take our joules of work, so 187.5 joules, and divide that by the time of 2.0 seconds equals, and we'll see if it equals 93. So 187.5 divided by 2.0, we get 93.75 watts, which is basically what they are saying in the problem. So yeah, that is true. All right, number 5. How much work is done when a 5 Newton force moves a block 4 meters? Okay, so we have our equation for work given right here, which we copied from above, because that was also given up here at the top, okay, in this little box. So we know that work is equal to force times distance. Our force in this case is going to be, oh geez, what the heck? What's going on with my tab thingamajigger? Anyway, 5 newtons times our distance of 4 meters. We can do this on a calculator, but I can do this in my head. So it's going to give us 20, and the units for this will be joules. So 20 joules of work will be done. Number 6, how far will 350 joules raise a block weighing 7 newtons? So, again, we know that work is equal to force times distance. Okay. If we want to solve for distance, so in this problem we are given 350 joules of work, which is equal to 7 newtons of force times some amount of distance, and the question of course is, well, what's the distance? So we can see that we need to get the variable distance by itself. It's being multiplied by 7, so in order for us to solve this, we need to divide this side by 7 newtons. That will cancel out, I don't know how I do the shortcut for this. Let's do that. There you go. It'll cancel out the 7 newtons there and cancel out the 7 newtons there. If we divide the right side by 7 newtons, we need to divide the left side by 7 newtons. So we'll divide 350 by 7. So we're basically going to get 350 joules divided by 7, which is equal to 50. And the distance will be meters. And that will be our distance. Okay, so 350 divided by 7 gives us 50 meters of distance. All right, number 7. How much power does it take to do 104 joules of work in 8 seconds? Okay, so we know that power is equal to work divided by time. So in order for us to solve this, we need to know that power is equal to 104 joules of work divided by 8 seconds of time. Just a basic division problem. So 104 divided by 8. We get 13, and the units in this case are going to be watts. Okay, so 13 watts of power is what we're looking for. All right, number 8, which is more work? Pushing with 115 newtons over 15 meters or lifting 20 newtons 10 meters. All right, so again, work is equal to, why did my font change? I swear, man, technology these days. All right, work is equal to force times distance. In the first example, we have 115 newtons of force times 15 meters. So this is probably going to be a very large number, but let's see here. So 115 times 15, we get 1,725 joules of work. So that's work. We'll say this is oh man, I'm doing all kinds of stuff. What are we doing here? Stop. Work 1. Oh. There we go. Okay, so this is like the work 1. This is the first work. And then the second one, so this is going to be work 2. And this is 20 newtons times 10 meters. And I can already tell it's not going to be as much, but 20 times 10. 20 times 10. There we go. We get 200 joules. So of the two, which is more work? Pushing with 150 newtons over 15 meters is more work. So let's go back to red, change the font to the right type of font. There we go. Pushing with 115 newtons over 15 meters is more work. Okay, and we have the math again shown right above. All right, moving on to 14.2. Number 9, if a machine has a mechanical advantage much larger than 1, its output force is... all right, so mechanical advantage means that that machine is taking the force you're putting in and it's multiplying it by a certain factor. So like it's making, it's taking your force and it's multiplying it by 1 or by 2, so it's doubling your force, or by 3, so it's tripling your force. So in this question, it says if a machine has a mechanical advantage much larger than 1, the force it's giving out, okay, its output force is going to be a lot larger than the force you're putting in, okay? So your input force is going to be much, much less. So of our choices here, its output force is going to be much larger than its input force because it's essentially taking your input and it's multiplying it by a lot, okay? All right, number 10, how is the work output of a machine related to its work input? So we have to remember that a machine's work output is always going to be less than the work input because you're going to lose some work due to friction, okay? So the work output will always be less than its work input, again, because of friction. All right, number 11, a machine you designed has input and output arms that pivot around a fulcrum. Okay, so we have a lever. When the input arm is pushed down through a short distance, the output arm moves down through a longer distance. Is the output force less than, equal to, or greater than the input force? All right, so this concept is based on how force and distance work in machines, okay? So the main thing we need to remember is that force and distance are opposites from each other in terms of how machines work. So basically what we're saying is if force is increased, then distance is decreased. And if force is decreased, then distance is increased. Okay? So this machine, you have an input arm and it's pushed down through a short distance, okay? So the distance is small. The output arm then moves through a longer distance. So basically what it's doing is it's taking your short distance and making it a long distance. So the distance that you are doing is increasing, okay? So is the output force then going to be less than, equal to, or greater than the input force? So if taking the distance that you're putting in and it's increasing it, that means that the force you're putting in is going to be low. Okay, it's decreasing your force. So the output force that it's going to be giving out is going to be a small force, and the amount of force you have to put in is going to be a large force, okay, because they're opposites. So again, we're going to be trying to make sure that this makes sense, okay? Okay, I'm trying to do a visual here. So, input distance is small in this example, okay? Because you're putting in a small amount of force, which means that, let's shift this down too, it's on the way. Okay, so if input distance is small, that means that input force is large, okay? So you put in a small distance, but the amount of force needed is going to be very large. Likewise, if output distance is large, then output force is going to be small, okay? So this question is again asking, is the output force less than, equal to, or greater than the input force? The output force is going to be less than the input force. Okay, so you're going to have to put in a very large amount of force to push this thing, and the force you're going to get out on the other end is going to be a lot weaker. So hopefully that makes sense, but that is our final answer. So we will say make this is red. There we go. You'll say the output force is going to be less than the input force. Okay? All right. Hopefully that makes sense. All right. 14.3. So now we're dealing with mechanical advantage and efficiency. Number 12. A machine with a 5 Newton input force and a 25 Newton output force has a mechanical advantage of... Okay, so we are calculating actual mechanical advantage. They're giving us an input and an output. So we're just going to take output divided by input. So 25 divided by 5. That will give us a mechanical advantage of 5. Number 13, if you know the input distance and output distance of a machine, which of the following can you calculate? All right, so if we're given input distance and output distance of the two types of mechanical advantage, ideal mechanical advantage deals with distances. So automatically I already know that this is going to be letter D as our answer, because actual mechanical advantage deals with forces. And these two things don't deal with either. So, all right. Number 14, a 100-meter long ski lift carries skiers from a station at the foot of a slope to a second station 40 meters above. What is the ideal mechanical advantage of the lift? All right, so it's basically a ramp, okay? The 100-meter long ski lift is the distance that the 100-meter long ski lift is the distance. I'm sorry, I'm just blanking here. Gotcha. Okay, so the 100-meter long ski lift is going to be the distance that the machine has to carry you, right? And the 40 meters is going to be the output. Okay, so this is the output. This is how much. Sorry, this is how much the machine is essentially lifting your body, and the input is how long like you are having to like ride this thing. Okay, so this is your input, 100 meters. Your output is 40. So to determine our ideal mechanical advantage, we can take our input of 100 divided by our output of 40, and we can determine what our mechanical advantage is. Okay, so we're going to take 100 divided by 40, and we get a mechanical advantage of 2.5. Sorry, I didn't mean to make that more confusing than it needed to be. Sorry. So again, the 100 meters here, this is your input. This is how far you have to travel. Okay, you are traveling up the ski lift. And the 40 meters given here is the output. That is essentially how high up the machine is like lifting your body. Okay, because it's essentially just lifting you like 40 meters up in the air. It's just doing so over like a longer distance. All right. Number 15, the efficiency of a machine is always less than 100% because, okay, so efficiency, again, is dealing with the amount of work you're putting in compared to how much you're getting out, okay? Now, you're never going to get out the same amount of work that you put in because of friction. So the efficiency of a machine is always going to be less than 100% because the machine, some input work is always going to be lost to friction to overcome friction. Number 16, a motor with an efficiency rating of 80% must supply 300 joules of useful work. What amount of work must be supplied to the motor? Okay, so you have a 300 joule, you have an engine with an efficiency rating of 80%. Okay, so 300 joules must be given into the machine to get it to work. Okay, so again, you must supply 300 joules of work. So you have to put in 300 joules, but you're only going to, oh, hold on, oh, sorry, what amount of work must be supplied? Oh, I'm sorry, I misread this. So 300 joules is what the machine's giving you out. The question, of course, is, well, how much do you have to put in? So if you're getting 300 joules out of it, that's only 80% of what you should be getting out of it. Okay, you should be getting more. The question, of course, is, well, how much should you be getting out? So looking at our choices here, just thinking for a second, it's not going to be A, because whatever amount of work, so whatever work we put in has to be more than 300. Okay, because again, we're not going to get out as much as we put in. So it can't be A and it can't be B. So it's either going to be C or D. So 375 joules. If we take 375 joules and we multiply this by 0.80, okay, so basically 80% as a decimal. If this is equal to 300, then this is our answer. Yeah. Okay. So we put in 375 joules of work, but we're only going to get 80% out, which is going to be 300 joules. And it does tell us right here that the machine is giving 300 joules of useful work. So basically, C is our correct answer. All right, number 9. If a simple machine could be frictionless, how would its IMA and AMA compare? So remember that ideal mechanical advantage is essentially the mechanical advantage of a machine without friction. And actual mechanical advantage is the mechanical advantage of a machine with friction. So if a simple machine could be frictionless, right, have no friction, the IMA, which is the ideal mechanical advantage, and the AMA, the actual mechanical advantage, would be exactly the same. Okay, so we can say if there were no friction, oh, I can't type friction, there we go, then the IMA and AMA would be exactly the same. All right. Number 18, the input force of a pulley system must move 6 meters to lift a 3000 engine a distance of 0.50 meters. What is the IMA of the system? So what is the ideal mechanical advantage, which we know is input distance divided by output distance. Okay, so this is our equation for ideal mechanical advantage. So basically, we just need to determine, well, what's the input distance, what's the output distance in this problem. So it says here that the input force of a pulley system must move 6 meters. So we are inputting 6 meters of distance. Okay, so we have to pull 6 meters. So this is our input. To lift an engine, a distance of 0.50 meters. So we're only lifting it half a meter. Okay, that's our output. That's what the pulley is lifting for us. So to determine our ideal mechanical advantage, we are just going to essentially take 6 meters and divide that by 0.5 meters, and we will determine our mechanical advantage. Okay, so it's a basic division problem. So 6.0 divided by 0.5, and we get 12 as our mechanical advantage. Okay, ideal mechanical advantage. All right, number 19, a 16 Newton force applied to the handle of a door produces a 30 Newton output force. What is the AMA of the handle? So what's the actual mechanical advantage of the handle? Okay, so our actual mechanical advantage equation is given up above. So let's just copy paste it down here so we have it. Put it in red. Okay, so we have a 16 Newton force applied to the handle of the door. So if we are applying 16 Newtons, that is our input force. And the door produces a 30 Newton output force, right? Which is even says output force. So to determine our actual mechanical advantage, all we're going to do is take our output force, which is 30 newtons, divide that by our input force of 16 newtons, and we will get a mechanical advantage. So 30 divided by 16, we get a mechanical advantage of 1.875. We'll just say 1.9. Here, just round to 1.9. 1.875, 1.9, same thing. All right, number 20, which is not a simple machine. All right, so simple machines, there's 6 simple machines, okay? So there's levers, wheel and axle, incline plane, screw, wedge, pulley. Of those 6, the fulcrum is not a simple machine. That is a part of a lever, okay, but it is not a simple machine in itself. So it is the fulcrum. That is not a simple machine. All right. Just going to reformat this. Sorry. Okay. Levers. Identify the class of each lever in the drawings. All right. So the different levers are based on where the fulcrum is located, where you are inputting force, and where the heavy part is that you're trying to move. So it even actually shows here first class, second class, third class. So first class lever, the fulcrum is in the middle. So with pliers, the fulcrum here is this little point in the middle, and then the input and the output are on opposite ends. So the input, of course, is where you push on the handles. The output is the part over here that's squeezing on something. So pliers are going to be a classic first class lever example. Okay. A broom. Okay, so a broom. The pivot point of a broom, okay, if you think of sweeping, like using a broom, right, sweeping, the pivot point is actually the top of the handle, okay, very top. That's where it pivots from. The heavy part is at the bottom. That's the broom, head itself. And then the handle is where you grab in the middle. So if we look at our classes of lever, this is going to be a third class lever because our fulcrum is at the end. We're grabbing in the middle. The heavy part's on the other end. So this is a third class lever. A fishing pole. All right, so fishing pole. So fishing pole, right, you grab it and you throw like this. So it's actually pivoting from the base, okay? This is the part that pivots, is the base of the fishing rod. You're grabbing it here. So this is your input. So fulcrum, input, and then the heavy part's at the very end. So this is actually just going to be like a broom. This is a third class lever where, again, you have your fulcrum at one end. You're grabbing it in the middle, and then your output, your heavy part, is at the other end. All right. And the last one, 24, is a wheelbarrow. So this is going to be a second class lever. Second class leverage, you have the fulcrum on one end, the heavy parts in the middle, and then you're lifting on the other end. Okay, so again, fulcrum's at the end, heavy parts in the middle, you're lifting at the other end. That is a typical second class lever. All right, number 25, what would be the IMA of the levers shown in the images below? So IMA, again, is the ideal mechanical advantage, which we have the equation for right up above here. So I'm actually going to copy paste this. So copy and paste. So we have it. So boom, there we go. All right. So for the first class lever, we are going to take our input distance, which is the distance from the input to the fulcrum. So in this case, it's 1 meter, divided by our output distance, which is from the output to the fulcrum, which in this case is also 1 meter. So we are going to get an ideal mechanical advantage of 1. Okay. As for the second class lever, our input distance is 3 meters. So that's from the input to the fulcrum. Our output distance in this case is 0.5 meters. Again, that's from the output to the fulcrum. So 0.5 meters. So to find our ideal mechanical advantage, we will take 3 divided by 0.5, and we will get an ideal mechanical advantage of 6. All right, and then third class lever, our input distance in this case is 0.7 meters, so much smaller. Our output distance is 2.2 meters. So to find our mechanical advantage, 0.7 divided by 2.2, and we get 0.32. So a mechanical advantage less than 1. Okay, and actually all third class levers will have mechanical advantages less than 1, which basically means that it takes more force to use them than it would if you were just to move the object by yourself. But the upside is that third class levers gives you more distance out. Okay, that's what you're trading. So you have to use more force, but you're getting more distance out of it, which depending on what it's for is good. So, all right, number 26, supply your knowledge about wheel and axles. Which would be the better choice for driving a screw into a board? A long screwdriver with a narrow handle or a short screwdriver with a wide handle? Okay, so wheel and axle. Mechanical advantage for wheel and axle is going to be like a lever where we're going to have input distance, output distance, okay? The input distance is going to be the radius of the wheel. And the output distance is going to be the radius of the axle, okay? So if we want to have a large mechanical advantage, which essentially means that it's easier for us to turn the screwdriver, we want to have a large wheel and a small axle. So a long screwdriver with a narrow handle. Okay, the handle is the wheel. The screwdriver part is the axle. So narrow handle is not going to be very good because it's not wide. Okay, and that's the wheel radius. Whereas a short screwdriver with a wide handle is going to be a lot better because the wheel is bigger, right? Bigger radius, which essentially gives you larger mechanical advantage. So in this case, the short screwdriver with a wide handle will give us the best mechanical advantage. Okay, so that is that one. All right, almost done. Number 27, what is the ideal mechanical advantage of this inclined plane? All right, so ideal mechanical advantage we just had right here. Just going to copy paste this one more time. Bam. Oh, that kind of messes things up. Let's not do that. Let's just do this. Let's just shift this down. There we go. We'll do it there. Boom. There we go. Obviously, we're not talking about wheels and axles anymore, so let's get rid of that. Okay. So ideal mechanical advantage is input distance divided by output distance. Input distance is going to be the distance that you have to push this object up the inclined plane. The output distance is the distance that the inclined plane is essentially lifting it for you. Okay, so in this case, our IMA, or ideal mechanical advantage, is going to be equal to 13 meters divided by 3 meters. And that will tell us our ideal mechanical advantage. So 13 divided by 3, and we get 4.33 as our mechanical advantage. All right, number 28, what is the efficiency of the inclined plane shown below? So efficiency, which actually I realized the equation is not given to me on my sheet, but I'm going to give it to you on your sheet. So if you're watching this video, it is on your sheet. But efficiency is going to be, I can't spell efficiency, there we go, is going to be equal to work output, or output work, divided by input work. I cannot type right now. Output work, or input work. And then we're going to times all of that by 100%. Okay? So in order for us to determine efficiency, we need to calculate the output work and the input work. And we know that work is equal to force times distance. Okay? So input work is going to be input force divided by input distance. And output work is going to be output force divided by, times output distance. Okay, so we've got all these things. We just need to basically figure out what's the input, what's the output. So the input distance is going to be the distance we have to pull this object up the ramp. The input force is the amount of force we have to use to pull the object up the ramp. Okay, so it's going to be input work is equal to 8 meters times 300 newtons. Okay, because that's the distance here that we have to pull this thing up the ramp and the amount of force we have to use. So we will calculate this real quick. So 8 times 300. So 2,400 joules of input work. All right. As for our output work is going to be 3.5 meters times 550 newtons. So we have, the ramp essentially is lifting this object 3.5 meters vertically, and it's 550 newtons of force to lift it. Okay, so that's our output. So 3.5 meters times 550 newtons. And let's see what we get. So 3.5 times 550, we get 1,925 joules of output work. All right, so once we have those two things, then our efficiency is going to be our output work of 1,925 joules divided by our input work of 2,400 joules, and then times that by 100% to get an efficiency rating. And it's not going to be 100% because it never will be, but hopefully it'll be close. We get an efficiency of about 80%. Okay, so about 80% out, which isn't bad. All right, number 29. We have 2 questions left here, guys. How much force would you need to input on this rope in order to lift the object shown in the image below? All right, so we have a 79 Newton object. And the question is how much force do we have to pull on this rope to lift it? All right, so to determine that, we need to know what is the mechanical advantage of this pulley system. And that can be determined by counting the number of ropes that are pulling up on this pulley system, okay? Or that are pulling up on this object. So if we count the ropes here, we have 1, 2, 3, 4, 5, 6, 7 ropes pulling upwards. So this is going to have a mechanical advantage. Okay, so this pulley has a mechanical advantage of 7, which means it will take 7 times less force to lift this object. So if our object is 79 newtons of force, okay, so 79 newtons of output force divided by 7, which is our mechanical advantage, that will tell us how much force we need to use to lift it. So 79 divided by 7, we get 11.3 newtons of input force will be needed. Okay, so 11.3 newtons of force will be needed to lift this 79 Newton object. All right, last question, basically the same exact thing as number 29, just different pulley system. How much force will you need to input on this rope in order to lift the object shown in the image below? So again, in order for us to determine this, we need to know the mechanical advantage. So the MA of this pulley system is, so we need to count the number of ropes lifting upwards. We have 1 here and a second one here. This rope is pulling downwards, so we do not count this for mechanical advantage. So we just have 2. So in this case, the mechanical advantage of this pulley system is 2. So it's going to take basically 2 times less force to lift it. So we're going to take 175 newtons and divide that by 2, and that will tell us how much force is required to lift. So we have 87.5 newtons of input force is needed. Bam, there we go. All right. So that was the last problem. Hopefully this helps you understand a lot of these concepts. I know it took a while. I appreciate you sticking with me for it though. And of course, if you have any other questions, please do not hesitate to email me and reach out and ask. All right, guys, I'm Mr. B. Thanks for watching, and I will see you in the next one. Bye.